The next session is going to be about innovative applications of statistics, machine learning, and AI. We have distinguished speakers: Ed George from the Wharton School at the University of Pennsylvania, emeritus; Tian Zheng from the Department of Statistics at Columbia University; and Aji Boissodieng from Princeton was scheduled to talk, but unfortunately, she had a cancellation. She didn't feel well at all. And so Aji, if you're watching, we hope you feel better. So let's welcome Ed George.
Thanks, Edo. Super. Wonderful. Everyone can hear me just fine? Oh, look at that. All the thumbs up. So, yeah. I'm completely delighted to be here. This is a great conference. I was lucky enough to speak at it last year and enjoyed it thoroughly. Thank you so much, Edo. Thank you so much, John, Leon, you guys at Wells Fargo and Temple. Also, a shout out to Summer and Tava, who have been just wonderful, making my life easy and making this work so well. It's just brilliantly run. Anyhow, what I'm going to talk, and now for something different. This is going to be a talk. Here's the title of it. It's about estimating hospital mortality rates. And I call it calibration and standardization for public reporting. So my focus is on mortality rates across, you'll see, 4,000 hospitals. This is an application, okay? So I'm going to show you now that we're going to take real data and we're going to sort of apply statistical methods to it. I love applications, even more than I work on methodology and theory and stuff. But the thing about an application, when you get real data, that's where the rubber meets the road. And you have to really figure out what methods you're going to use. Not necessarily the most spectacular method that there is. You have to do what you need to do. And you're just faced with the sort of reality of data. Now, there's a narrative to this whole talk, which I think is totally fun. It's going to run like a detective story. There is some Medicare, publicly available data, which analyzes, the Medicare records that they have, and it gives you wrong mortality rates. There's something wrong, okay? And what we do is, I'm going to run it. It's a detective story. We're going to try and figure out what went wrong, how to fix it, and then we do fix it, okay? And in fact, you'll see that there's a murder weapon along the way, and I'm going to have to tell you about that murder weapon right at the beginning so you can recognize it when it comes up. Let me mention also my collaborators. We're going to talk about collaboration later in a panel. So this is actually a wonderful collaboration. I love all of these people. Veronica was my postdoc. Paul Rosenbaum was Don Rubin's very famous student. Vila was a graduate student at the time. And Jeff Silber, he's an important character in this. He's a doctor in the medical school, okay, I think at CHOP. And he's a terrific statistician, works in public health. But it turns out he was the one who recognized what was wrong with the Medicare data. And he went ballistic. And he's so funny. It was just so much fun to see him get so mad. And we have to fix this and whatever. So he was a driving force. So anyway, without further ado, let me begin. And I told you the first thing I have to tell you is the murder weapon. So here, now, the whole talk is not so technical, whatever. But I just want to give you a cautionary note about shrinkage estimation. Remember, we heard Ken mention shrinkage estimation, and it comes up in Bayesian methods. Naturally, you end up shrinking towards some target in order to borrow strength in an effective way, because that's what statisticians like to do when you have lots and lots of data. And one of the most basic models, this is like Bayes 101, is you just observe. Right, you have some data, let's say P observations of X, and you're going to say they each have different means, and each of them comes from a normal distribution with possibly different variances. So this is a basic setup, right? It's going multivariate from the univariate normal distribution. This is the multivariate normal distribution. And everything's independent here. And a basic thing people would do is they say, okay, let's start off by combining these things to say that perhaps all of these means are related as IID, that means independent draws from a same normal distribution with the same mean and the same variance. It's very basic. It gets things working. Lots of theoretical work has been done with this problem. Your goal there is to try and estimate how can you use this information to get a Bayes estimate of these mu's. Well, the kind of shrinkage estimators that arise look something like, I mean, there's fancier things than this, but they basically are going to be a weighted sum of the data itself and an estimate, let's say x bar, an average of all the x's, of that grand mean. So it's a trade-off, right? You're going to see, and it turns out one important aspect of this weighted sum, right, these coefficients sum to 1, is that mu I will strongly shrink xi towards x bar when the variance of the thing is really much larger than your estimated variance, right? So there's a lot of mechanics going into this, but when you finally get there, if you can't measure this thing very well and you use this model, it's going to say, look, you're better off putting all your eggs on in the x bar thing. And it's great, terrific properties. People thought, oh, you know, it's just, you know, under certain settings, this thing is just, you have nothing to lose by doing this. However, okay, unless you can safely assume that these all have the same prior mean and the same variance, this can be a disaster, okay? So the murder weapon, okay. Now let's continue. So this now will get to be fun. Not that that wasn't unbelievable fun. So here's public reporting of hospital mortality rates today. This is Medicare's website. Medicare has a website called Hospital Compare, and the goal there is they say, provide the public with all information on how hospitals in your area care for their adult patients with certain medical conditions. And you can see that website. I'm going to show you that website for the condition, is it AMI, heart attacks. Okay. So this is now a typical Medicare mortality rate report. And it's the death rate. It tells you the death rate for heart attack patients. You might log in and say, hey, I'm in Philadelphia and I'm interested in the University of Pennsylvania Hospital, Thomas Jefferson, or maybe Our Lady of Lourdes Medical Center. And here's a typical thing that they would show you. I've got this line here. This is the overall mortality rate. Which is death within 30 days of admission. Okay. The overall mortality rate across the United States by patient is about 15%. Okay. So, but anyhow, notice that these things, they're not all too different. And these are uncertainty intervals for each of them. And you can kind of see that they kind of overlap. I'll just mention that notice there's different number of patients at each of these in the AMI unit that are being done. And that's a relevant observation coming up. But here's the thing that where Jeff Silber, the doctor, started to go bananas. Hospital Compare, 2008, said out of 4,300 hospitals in the US, 4,300 of them are no different than the US national rate. All the hospitals are roughly about the same in terms of their mortality rate, okay? And 0 were actually worse. I think the remainder were all better, okay, which is a little nuts. And how did they reach these conclusions? Well, basically what they do is they want to borrow strength from mortality rates of different hospitals. And if you have a small hospital where, you know, maybe there's only 3 or 4 patients, so maybe you're going to have 0, 1, 2, 3, or 4 deaths, right? There's a lot of, they're very noisy. Well, they're going to borrow strength and they're going to shrink everything towards the overall mean. So they're basically pooling to give more confidence in the results. What's dangerous about this is this approach is being copied as a gold standard for general performance comparisons. So what's happening, well, you're going to see that this allows small hospitals to get away with murder, literally, okay? What Jeff said is, hospital compares estimates contradict the conventional wisdom that mortality rates are higher at low-volume hospitals. He asked most doctors or for advice on, if you need some kind of surgery, you want to go someplace where they do it a lot. Practice makes perfect. And so it just can't be the case that the mortality rates overall should be the same throughout. Okay. Well, here now I'm going to first show you, this is now a first look at the data. Okay. So this is the hospital compares reported mortality rates by volume. There's over 4,000 dots here, and each dot is the mortality rate for a particular hospital. This is the raw stuff. So notice that if a hospital had 5 patients in it, right, there's only, 5 possible values for that. And we know, right, if you only toss a coin a few times, the number of heads and the number of tails, right, can be all over the place, right? But if you keep tossing it, it will get to the long-term average, and that where. So these are just the hospital averages, and they're quite variable. But this variability is not unreasonable because I don't have many patients here, and as I get more and more patients, it tightens up. This red line was that 15 or 16%, I think, overall mortality rate in the population. No, 15%. It's at 15. Okay. This green line is actually, it's just a smooth, it's not a fit of a model. It's just a kind of a running mean, so you can kind of get a sense of where are the mortality rates on average higher up here, and then do they get lower as the hospitals increase? Oh, I should have mentioned, I've plotted these along their volume, along their size. So this is a hospital of size 1,000. This is a hospital of size 1. It's kind of the log scale, so everything's compressed down a little bit. But you get the picture of what's going on. Now, after Hospital Compare does their analysis, this is what they report. We think that from this data, a better estimate of the true mortality rates are given by this. It's crazy. All of a sudden, all of these points are really shrunk, and this is where all the small hospitals having the same mortality rate. And now as you get bigger, they spread out more and stuff like that. So this is now what you have, and I'm going to walk you through this stuff. This is really a practical application to real data. So first of all, we had to figure out what is it that they did. And Hospital Compare, they began with a log linear random effects model. I'm going to show you that to get a prediction of hospital mortality rates. So there's 2 steps, and then they do another step. They standardize them to adjust for patient case mixes. In all of these hospital comparisons of different hospital mortality rates, you have to take into account that maybe some hospitals have much sicker patients. So just because their mortality rate's worse doesn't mean that it's the hospital that's bad. It could be the patients. So you have to figure out a way to standardize things so that you can compare. And many of you have probably seen standardization in elementary statistics where you just subtract the mean and divide by the standard deviation. It's more sophisticated than that. But you want to be able to sort of have some measure where you can reliably not worry about the case mix effect that's driving the variation. Okay, so I'm going to show you those big things. Now, this next slide, I'm going to show you the next slide is showing you sorry. Let me look at the slides rather than tell you what's coming. So this is the data. This is the data that I'm going to be, I see what the problem is there. This is the data that we use to do our analysis, and it was the data that I just showed you. Okay, so we have Medicare data. These are electronic billing records. It's kind of interesting as a source of data. The billing records are great because they're not going to be biased to try and make things look good or bad. They mostly want to bias it so they can get what they're accurately paid. But in any case, I have Medicare data goes from July 1st, 2009 to December 31st of 2011. So we have 3 years of data. We have about 380,000 patients. So numbers are large, right? And they're admitted to 4,200, almost 4,300 hospitals. Look how many deaths there are, 56,000, about 15%. So in this business, right, 1% is an awful lot. So, because you're talking about deaths. So it behooves you to sort of be accurate about it. We also, what came with this data is not just whether they died or not, but for each line, you get what the patient characteristics were, right? Their age, whether they had a heart attack in the past, did they have a high blood pressure, et cetera. So these are comorbidities, things that you might worry about that might influence their mortality. And also, we had 4 hospital characteristics in this data. So we have the volume of the hospital, that was what I did in my plot before. We also have the resident to bed ratio. We have the nurse to bed ratio. By the way, resident to bed ratio is it a teaching hospital, right? So you often have many residents in teaching hospitals, stuff like that. Nursing is, how many nurses are there to sort of aid. And there's been some controversy about, are nurses valuable? I think it's kind of more and more evidence shows that nurses are absolutely essential for reducing mortality rate. And this PCI, this is, I forget the name that it stands for, but it's, can they do this cabbage operation? It's like stent or very fancy kind of technological things to sort of cope with problems that might arise. We also, to be good statisticians, I guess it's 2.5 years of data, I should have said. And we kept the first 2 years as training data, and then for validation, we kept the last 6 months, and we really kept them out. We built our models completely, and so you kind of hold your breath at the end when you apply it to the stuff, and it's just wonderful that it works. Anyway, as you'll see. Okay, now I'm ready to tell you. Remember, I said before, if I go to step 1, okay. I said hospital compare begins with the log linear random effects model to predict hospital mortality rates. So this is now the model. This is the model they use. And this P is the probability of dying within 30 days of admission, okay? And it's patient J in hospital I. So I used H for the subscript because that refers to the hospital you're in. And we're saying that the logit transform of this probability is just a easy linear model, but with these random effects, there's going to be a hospital effect here, and then these are going to be the patient effects. Remember I said there were 27 patient characteristics? Well, we put them all in this vector, and then we have a coefficient there. So these are often called random effects and patient mixed effects. And a traditional way of modeling these things often has been to simply make these as random draws, let's say from a normal distribution, right? And have them be IID. Notice that that's in red. And if you remember, we go way back, the murder weapon's in red too. So anyhow, so we'll go on. Okay, so this is just how the model, and you can fit this model, and they actually fit it by constrained maximum likelihood. It's like Bayesian with a flat prior. Actually, George Box had this wonderful statement. He said Bayesian analysis with a maximum likelihood is a coward's way of being a Bayesian, so which is a fun remark. But in any case, okay, so here. This kind of looks like what I showed you before. This is the fit of hospital compare to that data. So I'm going to go back. Here's the data right up here. And now if I go, here's the fit. It looks kind of the same, but now this goes from 0 to 0.8. So things have been shrunk considerably. These are the predictions after using that model. Okay. So and basically each of these dots is the sum of the probabilities that you get from the model, and they've really shrunk, right? This shrunk way down from before where they were way up top. So there's quite a bit of shrinkage that was going on, but more so, look what happened to the alphas. these are the hospital effects. They got shrunk tremendously. And especially the large alphas, the large hospital effects got shrunk way down because you're wanting to know what is the mean, essentially, right, of those values. This looks an awful lot like that second plot I showed you, but we'll talk more about the connection between those two later. But under this model, the mortality rate variation at small volume hospitals, this variation that we're seeing here, has to be being driven essentially by patient mix differences. Okay, so one hospital here has high mortality rate, probably unhealthy patients, et cetera. So there's a lot of variation of these, which is going on. Okay. Now, one question to notice, to think about with what's going on here is, as I mentioned, hospital effects have been modeled exactly by this normal, IID normal model. They're completely random with the same mean and variance. So you're building in that on average, all models, right, are equally dangerous, okay, and have the same variation. And, it may be from that we saw that the mortality was declining as volume went up. Maybe that's not so reasonable. And also, as we saw, this is leading to the strong shrinkage of the alphas for the small volume hospitals. Remember I said if the variance is very large when you model these things with that normal prior, what's going to happen is when there's a huge amount of variance, okay, and in fact maybe I'll even go back if you'll bear with me a second, but right, here's the data. If this variance is large, and this would be something, if I just had 3 or 4 patients, I have a large variance observation. If I have 100 patients or 1,000 patients, okay, there's not going to be much variance here because of things, the law of large numbers, stuff like that. So in any case, if this is very small, I'm going to shrink tremendously towards there, and that's exactly what looks like what's happened here, okay? It's exactly what looks like what's happened there. Okay. Okay. Another aspect to sort of point out here, and this was a big bone of contention with because we were in touch with the hospital compare people, whatever, but they have left available hospital characteristics out of the model. Volume, nurse to bed ratio, resident to bed ratio, PCI, those were not even considered in their model. They're just not there. Okay, and the proponents of them, now politics is coming into play because I think Congress people actually don't want them. They really somehow want to test the hospitals to see how well are they really doing. And so they think it's kind of unfair to include something like volume in the model. Okay, but we would say, isn't excluding hospital characteristics unfair to the people who want to seek accurate information? Okay. Okay. Now I could say this one thing. So when we evaluate the performance of our students in a course, on an exam, right? What we do is we look at how well they performed. Sorry, in a course, we look at how well they performed on the exam. But you don't take their exam performance and then adjust it for all the different other courses they took and stuff like that. You could probably get a better estimate. But they're kind of arguing, look, we should just view the mortality rate as one exam of these hospitals, and they're thinking about funding for the hospital and stuff like that. So those issues are sort of coming into play. But then they're telling people that these are the mortality rates that they might use for judgments, and so that's perhaps not so good. Okay. Okay. So will adding hospital characteristics make a difference here? Okay. So this is what we did. This is the next step. Okay. So what we did is we decided to take their model and we elaborated this normal part to this part to be this, where we actually let the hyperparameters of the normal model depend on the hospital. So we're just doing this. We're using the same model, but we're going to elaborate this to this. And what we did is we took, this is now just to make it easier on the eye, we're going to label the different 5 models we considered as CC, LC, SL, SLL, and this one here. And basically, CC means we treated this as a constant and this as a constant. We use this, which is essentially the same as hospital compare. Then the next step, the very first step, just to relax the assumptions, and I actually called it let's emancipate the means. Let's, in fact, for the first part, let's let this mu sub h be a linear function of the log volume. So basically, you're building into your model at this higher level. You're saying, OK, the mean is equal to some, let's say, gamma 0 plus gamma 1 times log volume h. And then we kept the variance constant. Here, going further, we tried a spline model to be more flexible than just a linear relationship. And then here, now there's spline, and now we put in the other variables. And finally, we did something with an interaction. But let me call your attention. It's this first one that you're going to see a remarkable change that happens. One of the most satisfying things, I think, in analyzing real data is when you find structure and it just jumps out at you. It's kind of, we say, letting the data speak. And in fact, you're going to see by going from here to here, all of a sudden, we really let the data speak. What's nice about all of these models is that each one, right, if I take each one of these is a nesting of this one. So linear is a special case of the spline, right? This one is a special case of this with no interaction, et cetera. Okay. And in all of this, we loved the fully Bayesian implementations just make this work. Okay. It just makes life easier. One thing we always tried to use non-influential priors, vague priors, and then there's things you have to do to adjust for this because you always have to be careful when you're trying to be non-influential. But it's not clear we had real subjective information to do this. Okay, and this has to do with calculations. I'll skip that remark. Okay, so here I just want to remember I said letting the data speak. This was the most phenomenal thing. When we did this, we jumped out of our chairs. The rest of the stuff is like a second order correction. But if you simply go from having a constant mean and you say, hey, let's let the mean have a linear relationship. And now you build it in the model, so it's now going to automatically fit. This thing just jumps wildly up, and you can easily see that you have higher mortality rates at the lower volume hospitals. So just by doing this, and all of a sudden, I mean, it's just obvious. You don't even kind of need statistics to see this. Just by adding the right term to capture the phenomena that's going on. Now here, we of course we went a little further. You get some improvement when you go to when you go to the spline, and then going further. Here's when I go to now not only the spline and linear with other variables in there, and you let the variance also model. And then here's the final thing with the interactions. It's interesting that this is a little thinner, but if there are questions about it, I could answer it at the end. But basically, these refinements continue to support higher mortality rates at lower volume hospitals. So basically, I'm just showing you, hey, this was our idea. Let's try this. And it looks like, oh my God, it's terrific. But just because it looks good doesn't mean that we're getting better predictions. So you actually have to do, right? What we did is have predictions really improved. And there are, principled ways to do this. One of the principled ways is to use Bayes factors, okay, where you're basically comparing the probability of your data given the model to the probability of the data given the alternative model. And what we did is we were interested in comparing, making those comparisons for the CC model with all the others. But one aspect here is we actually couldn't use in-sample Bayes factors. We actually have to use out-of-sample predictive Bayes factors versus this, and that's because we're using these It's a delicate issue, but it's because we're using these vague priors. They have very heavy tails, so they don't influence the estimation, but it turns out that the testing, you have to use sort of your out-of-sample data. So we actually compared these on the out-of-sample data, and here is just the log-based factor. This is comparing the linear to the CC model. This is comparing the spline to the CC. And you can see that means that e to the 27 is how much larger that probability is. So it's huge. And it turns out you are getting clear improvements, okay? So, no question, this is fitting the data overall much better. Okay. Now, turns out, and this is kind of Paul Rosenbaum, who's on there, who's a master of causal comparisons and stuff. He said, look, it's great. We know that the predictive Bayes factor is great for gauging the quality of the model predictions overall, okay? But what about calibration of model predictions with future mortality rates on particular segments of patients, okay? That is, maybe we should be worried that it's not doing such a good job in terms of predicting low volume hospitals. So what we did is we said, look, let's compare the patients at a low volume hospital and how they fared with patients at high volume hospitals, but we're going to take a subsample and we're going to match them. And watch this. This is kind of cool. So this is in the data, okay, but looking at the out-of-sample data, the observed mortality at the low volume hospitals out of sample was 28%, a lot larger than the 15%. At the high volume overall, it was 12.4%, much lower. So clearly, there's a lot more mortality at low-volume hospitals. But when you do the matching, that is, what we did is we said, let's actually take a subset of the patients at high volume and match them in terms of their characteristics to the patients at the low volume and see how they fared. Well, they did substantially better. So this kind of looks like high-volume hospitals, just from this comparison, are clearly worse. They're clearly worse. But they're clearly worse. But it's also, we can see clearly that the low-volume hospital mortality is not only due to the hospital being bad, but also the fact that they do have sicker patients. And just to compare our two models, you can see that the hospital compare model is really not predicting very well at the low-volume model compared to ours. And it's certainly not predicting so well compared to the high volume matched. So this predicted 23% when the actual observed was 28%. Okay. So I want to tell you a little bit, so I'm going to take an extra 5 minutes to talk about the indirect and direct standardization, because this is where causality comes into play. And it's kind of interesting, or maybe I shouldn't say causality, counterfactuals come into play. But this is a very cool idea. Okay. So as I said before, mortality rate at hospital age is influenced by the patient case mix. Okay. So what we'd like to do is standardize that to eliminate the effect of case mix variation. So I want to say in this hospital, can you give me kind of a purer measure of what the mortality rate is, adjusted for your the case mix of patients that are seeing you? And there's something called indirect standardization and direct standardization. I will mention both of them, but both approaches make use of the fact that the mortality rate for patient H at any hospital there can be obtained with this equation. Now, it's worth taking just a look at this. This is, when I write logit inverse, this is just sort of inverting that original random effects model, which was the logit of pH is equal to something. This is the logit of it. But it turns out what I can do is, for any patient, if I want to get their probability, I keep these variables, but I just substitute in what that hospital alpha was. Because I can estimate the alphas for all the hospitals. So if I do that with my model, and now I plug it in, I get an estimate of the probability of death. So notice with this, I can take any patient and send them to any hospital and see how they did. Kind of cool, right? And so that you've got your model, and now you can do the hypothetical. They only patient XHJ did in fact went to hospital H, but I can send them to hospital H star and see how they would do. So that's a counterfactual. Now, the two kinds of standardization, easy enough to show. Did I turn that? Oh. Are you trying to give me a hint? No. Okay. Here's what we do. So what we do is for indirect standardization, which was what Hospital Compare did, is they looked at the average mortality rate of hospital H patients had they been treated at every hospital. So they took all the patients which went to hospital H, and they sent them all to every hospital, or sought how and looked at what their average mortality would be there. So if they would have been better off at other hospitals, it's a lousy hospital. But if they would have been worse off, then it's a good hospital. And then a natural thing it would seem to do would be to actually just look at the ratio. This is how well they did it at their hospital, how well they would have done on average at all other hospitals. And then they just multiply that by 15%, and that was what they reported. And those are the things that I showed you when it was the hospital mortality rates that they actually use in their model. It turns out that there are some problems with this. And rather than go through that, because I'm looking at this is the mortality rates from indirect standardization. This was the first plot that I showed you. This is the mortality rates if I use this model, and there's still substantial variation here from case mix variation. So our idea, and we propose it in the paper as well, is to use what's called direct standardization. That is, instead of taking all the patients from hospital H and sending them to all other hospitals, why not simply take all the patients and send them all to hospital H? So how would hospital H have done if they had treated everybody? And now you know there's no case mix effect because they're all treating the entire population. It's a wonderful way to compare, okay? And it's just a natural comparison. And it actually is correctly calibrated to the actual mortality rates that you're seeing. So it's giving you a valid adjustment to all rates, okay? And what I'm going to suggest actually at the very end of the talk is that this is a way of taking data and kind of cleaning it or standardizing it so that you can now begin to do proper kind of, if you like, kind of unbiased assessment of mortality rates and the causes of mortality rates. And you can imagine doing this kind of thing in lots of other contexts as well. Okay. So this is now the adjustments that you get. Their hospital compare is kind of unchanged, but this, seriously, this sort of comes down and you're doing a lot better. Let me not, this is interesting with the, well, okay. The red horizontal line here is the average patient mortality rate, 15%. The blue line is the actual average hospital mortality rate. It's much higher. Why? Because some of the small hospitals have much higher hospital mortality rates. And you don't want to average over patients, you want to average over hospitals when you're really assessing what's going on. But look at this. This is kind of our final result. Look at we're predicting mortality rates of 25, 30% at the small hospitals. It's devastatingly different than the 15%. So, I mean, what the hospital compare thing is telling you is way off, okay? Because they've failed in a number of steps. Here, you get proper uncertainty quantification. I don't think I have time to talk about them. Here is just a little, if I do the hospital classification by mortality rates using our model, here, basically, you just see that hospital compare said, look, there were 33 were a little low, 30 were high, 4,300 are basically average. If you use our approach, what happens is you certainly have low are the good ones, by the way. Low is better here. So we have many more large hospitals are found to be good, but many more small hospitals are also found to be bad. So you're getting a much better reading of what's going on. And this is really my last slide, okay? So here, but this is what I want to tell you, is now these are the directly standardized mortality rate values. And now I have a whole lot of data which is properly standardized. And I can look at say the value of, these are the mortality rates now compared to did they have the high technology or not. This is the nurse to bed ratio. All of a sudden you can see that the values of nurses really, really lowers the higher the nurse to bed ratio, the lower the mortality rates. And here's direct evidence that patients fare better at teaching hospitals, okay? So, but the idea is now we have data that we can properly analyze when you do all of this. So it's terrific. Conclusions, strong evidence, hospital characteristics should be included in the model. Indirect standardization, I showed you that. Direct standardization. Here's a dilemma perhaps we could talk about in the questions. Should Medicare publicly report the alarmingly high mortality rates at the low volume hospitals? I mean, there are people who live in rural communities and that's all they have. So there's a real dilemma on just how to handle this. And that's kind of interesting. So thank you very much. Thank you for letting me go over.